Thanks for signing up for this course. I'm actually quite excited to cover what we're going to. It's seriously cool stuff, and I only wish we had had these things when I was teaching at the science camp. Some of it we did, but with the advent of both the internet and the open source movement, the things you can do now at home for dirt cheap is astonishing. In the first module, we dealt with the foundations for analog electronics, which are critical for understanding this module on digital electronics and in the modules to come, where we build a 3D printer, and the fifth module, which I've decided I am going to do, on autonomous robots. Now, the stuff we'll get into in that module will be wild, involving accelerometers like many smartphones have, receiving and using GPS signals, and the Altera chips, where instead of building a circuit like we did in the previous module, you design a circuit on a microchip. But I digress. First things first, we need to get an understanding in digital electronics. So just what is digital electronics? Why should we care? Why is digital so important? Let's say I'm trying to send you a signal with a wire. You're down at the garage, which is about 150 feet from the house, and we're conducting some kind of experiment involving water flow. I have a variable voltage supply in the house connected to that wire, and you have a voltmeter gauge on your end of the wire. We simply agree upon the communication. 1 volt means you need to run the water pump at 1 gallon per minute. 2 volts means 2 gallons per minute, 3 volts means 3 gallons, etc. So on my end of my experiment, I need more flow. So I crank up the voltage on the signal wire to 4 volts. However, because the wire is so long, there's that nasty voltage drop we talked about in the first module. Your voltmeter gauge actually only reads 2.5 volts. So you're down there going, huh? Does he want 2 gallons per minute or 3 gallons per minute? Meanwhile, I'm actually requesting 4 gallons per minute. So to solve this, we change our agreed upon method of communication. I send 4 pulses of voltage, which means I need 4 gallons per minute of flow. It doesn't matter what voltage you see on the gauge. You are simply looking at whether or not the gauge is 0 volts or some positive voltage, what we call a high signal. This is digital communication. Analog means the signal is infinitely variable. The voltage can be anything between, say, 0 and 10 volts. It could be 6.324 volts, or it could be exactly 2 volts. It's analog. With digital, it's either all or nothing. A high voltage or 0 volts. On or off. There is nothing in between. In the early days of telecommunication, the inventors of the telegraph figured out this problem and solution real quick. Instead of trying to communicate with varying voltages, they instead communicated using pulses of electricity. A guy by the name of Samuel Morse invented a pattern of pulses which represented all of the letters of the English alphabet as well as all of the numbers. This became known as the Morse code. The timing of pulses became a critical part of the code. A long pulse was called a dash and a short pulse was called a dot. It is a digital communication system. The signal was either on or off, voltage or no voltage. This enabled reliable and clear communication over thousands of miles of wire. Now, here on the Allenwater subdivision of what is now the CN rail line, the rail line and the telegraph lines were built in 1915. Repeater stations were located every 50 miles or so, which was just a building with batteries which took the weak digital signals and made them stronger to go across the next stretch of wires. In fact, the facsimile machine, better known as the fax machine, you know, that machine which can scan pages and pictures and print them out on another fax machine on the other side of the country. The fax machine was actually invented in 1843 and was the first commercial fax system, used mostly by news outlets, to transmit images for newspapers. It was introduced between Paris and Lyon in France in 1865 It used the telegraph system to transmit faxes, 11 years before the invention of the telephone and 21 years before radio waves were discovered and used for telegraphs. The first fax machine produced its images digitally. That's what the telegraph system used. It had a method of timing between the sending fax and the receiving fax. The receiving fax would move along the page and print a dot if there was a voltage, and no dot if there was none. It would print out a black and white picture composed of dots, just like our modern digital pictures painted with pixels. Now, believe it or not, the last telegraph system only shut down 3 years ago at the time of this recording. BSNL in India ended its telegraph service in July of 2013, only because the telephone network and a worldwide digital network known as the Internet made it obsolete. But the system still worked and worked well. Now, you can call the signal what you want. Call them dots and dashes, or in the case of digital electronics, it's a 0 or low for no voltage, and a 1 or a high for a voltage signal. In digital electronics, the voltage signal is typically the supply voltage, whatever that voltage is, and the 0, of course, is 0 volts. Now, you can get voltage drift on either end of the spectrum just because of the imperfections in the electronic circuit. For instance, nearby AC wires might induce a voltage on your wire, unless your 0 volts isn't actually 0 volts. Or you might have a long wire and thus your 5 volts is actually only about 4 volts. But it doesn't matter because the whole point of digital is for clarity of communication. As long as the voltage isn't close to, say, the halfway mark, 2.5 volts in a 5 volt system, then we can easily determine whether or not we have a high or a low. That's what we're concerned with here. No ambiguity. The system can be very forgiving of a lot of noise, and yet we can still get clear communication. With the telegraph system, they were able to get 3 different states. You might call them characters in the communication system. 0, and a dot, or a dash. Now, they did this by timing the high signal and making it either longer or shorter. In our case, we will have only 2 states, a high or a low, a 0 or a 1. We call this binary. Binary meaning 2. There are only 2 states, a high or a low, or a 0 or a 1. So a single wire can only transmit 1 bit of information, and that's our first terminology right there. That is a single bit. That's what we call that 1 or 0. It is a bit. All right, so 1 wire can do a job, but we can't do a whole lot with it. In the next lesson, we'll look at the different ways we can communicate more information digitally.